Welcome back. In today's lecture, I am going to talk about the bondedness and ultimate bondedness of the solution. Okay, and what is main motive? That whenever I have some kind of dynamical system, so suppose that dynamical system I am going to represent using this non-autonomous equation. So what we are assuming that this mathematical model is valid in some region, okay, and that region is subset of Rn, and we are also assuming whenever we are applying Lyapunov analysis that equilibrium point, and without loss of generality we are assuming x equal to 0 as a equilibrium point that is going to lie in this particular region D. Okay, now suppose the equilibrium point is not known to me, okay, or equilibrium point is changing with respect to time. So now question is that is it possible to apply the Lyapunov analysis to find the bond of this solution? Okay, so at least I can tell that, okay, even if I don't know the equilibrium point, but still I can tell that what is estimate of the bond of the solution, because whenever I have system, so I am giving some kind of initial condition xt0, and we are also giving explicit information of time, and after that we are getting xt because I have non-autonomous system. Due to that reason t0 I have written. So using Lyapunov analysis, if I don't know that x dot equal to 0 as x equal to 0, then we try to find some kind of bond on this xt, and we are going to see this bond as time is tending towards the infinity. It means that I am going to see the bond from for all t greater than equal to t0. Okay, and if you have gone through the linear control theory, you might have seen that whenever we are plotting the response, then what happens, suppose that if you have to track this point, so initially trajectory will go and overshoot, and after that some transient period come into picture, and when transient period come into picture, then what happens, whatever bond of the solution that is decreasing. Okay, so basically I have two different response in case of linear system. I have transient response and another is a steady state response. Okay, so once transient response is actually die, then what happens, that bond of a steady state bond that is significantly decreased in most of this system, not always. Okay, so due to that reason, if you are going to talk about this solution, then this solution has two different behavior. Okay, same like the linear system. So in some period of time it might possible that this bond xt solution bond is higher, but after some time it is possible to show that decrease to some significant value or some lesser value than initial. Okay, and this kind of behavior is very much common in the physical system. Okay, so main motive, main crux of the matter of the today's lecture, we are going to apply Lyapunov analysis, okay, in those situations where I don't know the equilibrium point, because whatever Lyapunov stability, asymptotic stability we have defined, at that time we have defined in terms of epsilon and delta. Okay, and what we found that whenever we are going to construct epsilon and delta ball, all ball I am going to construct with respect to equilibrium point. It means that I am assuming that equilibrium point is known to me, and then corresponding to any output ball there exists a input ball. Input ball means ball of xt0 I am telling. So if you start from here, you are going to stay there. So in order to construction of ball, somehow inherently we are assuming that I know the equilibrium point. Okay, now suppose this equilibrium point I don't know where that is. So is it possible to apply same kind of Lyapunov function to find the solution, or to see the futuristic trajectory, or to see the solution xt of this particular differential equation? That is the topic of the today's lecture. and answer is yes. Okay, so due to that reason, you can see that I have written here that first important quantity I am going to talk about, that is bondedness. And now you are able to understand that why I am going to talk about bondedness, because I have already told you that bondedness somehow reflect the some kind of stability. Okay, so if I have some kind of dynamical system, even if I don't know the equilibrium point, then what is my expectation that my trajectory xt is going to remain bounded by some value, some finite value. Okay, so now using Lyapunov analysis, one can show the boundedness of solution of the state of equation even there is no equilibrium point at the origin. Okay, so obviously I have some kind of equilibrium point that is varying with respect to time, because every time I can tell that okay, even if I have dynamical system, then rate of change, when rate of change equal to 0. Okay, so it might possible rate of change equal to 0 along some trajectory, that is also possible. Try to see from this particular simple expression. So I have taken a scalar system. Here in this scalar system, as delta sine t equal to xt, what do you think? What is the situation? Sunidhi, could you please comment? If delta sine t equal to xt, then what is our situation? Okay, Sunidhi,
Yes, sir.
okay, could you please comment that if xt equal to delta sine t, then what is situation for this dynamical system, whatever given here?
Sir, it's a periodic nature.
No, just you can tell that x dot equal to 0 means rate of change equal to 0.
Yes,
It
yes,
means
rate of
that
change is zero.
x t equal to delta sine t, the equilibrium point. But you can see that here equilibrium point is also changing with respect to time, because I don't know what is behavior of sine t. Sine t might vary from -1 to 1. Okay, so I cannot exactly tell what is my equilibrium point. Okay, and due to that reason, people are telling that equilibrium point is not known to us. Anyone has confusion? It means that I am telling that equilibrium point that is going to lie between minus delta to delta. That kind of things I am telling. Okay, so I don't know exactly the equilibrium point, and equilibrium point not exactly at the equilibrium point. Equilibrium point means at origin. Okay, so now using Lyapunov analysis, I want to find the bond on this particular solution xt. Okay, so this is a story about equilibrium point. So I have to write like this: equilibrium point x star is going to lie between minus delta to delta. Okay. Now suppose I am going to start from this initial condition A, and here delta whatever this quantity is basically maintaining some kind of uncertainty. Okay, and this is very obvious thing. Whenever some system is evolving in a space, okay, there exists some kind of disturbance. Suppose that if you design some kind of quadcopter, okay, even if you can design any system, any robotic system or any system, finally they will go in field. Okay, and air is going to hit them, and you know that air is varying with respect to time. Okay, whatever uncertainty or whatever velocity of air, that is going to vary with respect to time, so they might hit our system. Okay, and due to that reason, that kind of disturbance is always obvious. Now one way to analyze the solution, that what you can do, you can solve it. Always I have told you that two way, that one way direct you can use the solution, and after that you try to use some kind of inequality. Okay, some kind of norm or some kind of absolute value. If you have one dimensional case, then absolute value is fine, otherwise you have to use the norm, notion of norm. Okay, so solution of this is not difficult. Why this is not difficult? Because you know how to solve this ax plus bu. Okay, so we know that solution of this is given by EA t minus t0 x t0 and t0 to t, and EA t minus tau bu tau into d tau, and this is exactly a linear system where I have substituted a equal to -1 and b equal to delta and u equal to sine t. Okay, so due to that reason I have written solution like this. Anyone has confusion on this, then please let me know. Okay, if you don't have confusion, then now what I am going to show, I am going to calculate the bond. So I have taken absolute value on both hand side. Okay, and if you after taking the absolute value, you can see that this quantity e power a t minus t0, that is always decreasing with respect to time. Okay, and a is some positive quantity, and after that now here sin t, I know that sin t is going to lie from -1 to 1, and due to that reason if you take the absolute value, then delta is positive, and sin t I can take the worst case, and worst case is plus 1, and due to that reason I have written like this. Anyone has confusion on this? Okay, now you have to solve this definite integral, and if you solve this definite integral, you can see that this kind of situation I have. So as t equal to t0, at that time this value, this quantity equal to 1, so you can see that, and this quantity is also equal to 1, and after that negative sign is there, so I can tell that xt is always for all t greater than equal to t0, that is bounded by less than equal to a. Anyone has confusion on this particular bond? Just you can see here that I have substituted t equal to t0, and since I know that this term is decreasing, again this term is decreasing. Okay, and maximum value of e power a t minus t0, if you substitute t equal to t0, that is basically 1. Okay, and after that this value is going to decrease. So due to that reason I am telling, and we know this kind of situation, A is always dominating over delta, and due to that reason I have written solution like this. Okay, now let us try to see the another situation. It means that which shows that solution is bounded for all t greater than equal to t0 uniformly in t0. You can see that why I am telling uniformly in t0, because now you can start with any time. Solution xt remains bounded by this a only, and bond is basically independent of the t0. So bond is not explicitly dependent on your time of experiment. Okay, now what I am going to see, same kind of information I am going to gather using Lyapunov analysis. Okay, so before going to gather that kind of information, I am going to comment one more thing. What we found that here whatever bond I have calculated, so for both period, means I have transient kind of behavior and steady state behavior, so we are assuming that what is worst bond. Okay, but it is possible to show that once transient period is passed, then bond of solution in most of time that is going to decrease, and due to that reason what I am going to do, I am going uh, to tackle that kind of situation, and somehow I am going to do the analysis once transient has passed. Okay, so due to that reason I am assuming that there exists some kind of b, and now since I am assuming a greater than delta, I am telling that in this situation and both are greater than 0, there exists some kind of a, b and delta that is greater than 0. This kind of situation I am going to assume. Okay, and if you fix b solution xt as a b, you can see from here that if I substitute b here, then I can able to find some kind of time, okay, when this quantity xt become b. Is it possible to find or not? Or here you can see xt, I will substitute b, then is it possible to find some kind of time when this quantity xt equal to b or not? Iram, could you please answer?
Yes, sir, we can.
Yeah, one can do, because exponential function is here, and due to that reason you can now see that I have done same kind of things. I am telling that xt less than b provided for all t greater than equal to t0, and if you take the inverse of exponential, then ln comes into picture, and at that time now you can see that as t I am not telling for all t greater than equal to t0, but t greater than equal to t0 plus some number, finite number, because a is greater than delta. So obviously this is positive and this is positive too. So due to that reason, there exists some more time. So I have to wait for some longer time to see the bond, and bond become this value, and this value is lesser than a. So due to that reason, we are telling that this bond is better estimation, okay, or less conservative estimation. Anyone has confusion? And that is obvious because I have taken linear system. If you see carefully, then during analysis I have just taken the linear system, I haven't taken the nonlinear system, or still I will extend this result for nonlinear system. So here, so whenever I have linear system, then I have two response. One response is transient, another is steady state. Similar kind of behavior I can expect from nonlinear system also. So once transient is going to pass, then I have better estimation of xt. Okay, and it is said that uniformly bonded, and whatever bond B is called ultimate bond. Okay, so in this case, if you are able to find some kind of less conservative bond, then we are telling that whatever solution that is uniformly ultimately bonded. Okay, and what is ultimate bond? I can define the explicit bond B. Okay, and you can see that I can come very close to delta. Why I can come very close to delta? Because I have to make sure that B minus delta should be greater than 0. So I cannot decrease, okay, up to B delta that is greater than B, and that is from here also you can able to see. Here, if you see this dynamical system, I have told you that how to analyze whenever I have x dot. Suppose I have x dot equal to minus x. So since x belongs to R, so you can take one real line, and you can see that everywhere x is positive, then x dot is negative. Okay, so I am decreasing like this, and similarly in this left hand side I have this kind of situation, because x is less than 0, x dot is greater than 0. Now what happens, I am going to add some term that is delta sine t. So what happens, in some case it might possible this term become positive, so I can decrease up to x equal to delta, but after some time my behavior become uncertain. Suppose this is dominating, so x is positive here, and it might possible in worst case x dot also that become positive. It means that now I cannot converge, I try to diverge, but outside I cannot diverge because this term is going to dominate. And this is suggesting that you can able to decrease B, but you cannot decrease B that is lesser than the delta. Anyone has confusion on this? Sunidhi, is it become clear to you?
Yes, sir.
Baby Dana, baby Dana, are you here?
Yes, sir. Yes.
So due to that reason, because this kind of terminology is very useful, because you can see that in every practical system I have disturbance. So at that time you have to write this kind of language, uniform ultimate bonded with ultimate bond, like this kind of in control society actually expecting this kind of language. Okay, and due to that reason I'm going a little bit slow, you can see now. What happens, that same kind of thing. So first way what I have done the solution. Second way I do not going to solve, and what I am going to do now, using help of Lyapunov analysis, I am going to do this same analysis. I am assuming I don't know equilibrium point. There exists some equilibrium point, but that is varying with respect to time. Okay, so there exists equilibrium point, but I don't know. That kind of situation I have now in another way. So what happens, I have defined, since this is a scalar case, so I have defined Lyapunov function Vx equal to x square by 2. Now what I am going to do, that whenever I am defining, you know that this is greater than 0 and x equal to 0, this should be 0, so both condition is satisfied. Now I have to check third condition, v dot, and v dot if you do, then x dot, and x dot in place of x dot, now I am going to substitute this dynamics delta sin t. Okay, so if you substitute this, then x square and x plus delta, this kind of situation comes into picture. Now what I am going to do, since first term is always positive, so here I am going to check the worst situation, because if that is negative, then that is going to support us, because v dot less than, we are expecting v dot less than equal to 0, that kind of expectation we have. But who is going to destroy our expectation? This term x delta sin t, and due to that reason I am going to perform the worst case analysis. So in worst case analysis, I am going to take the worst value, and that is plus sin t. Anyone has plus sign absolute value of x, because sin t is going to lie from -1 to 1. Anyone has confusion, then please let me know. Anyone? Now you can see that basically this term is going to destroy this kind of inequality. Okay, so near the origin, the positive term delta x dominate the negative quadratic term minus x square. We know that x square, if you are inside the unit ball, then unit ball 0 to 1, so x square become lesser than x. Delta is here obviously. So if delta is such that, suppose the value of delta x is more than x square, then what happens, that v dot that become positive. Okay, so always there exists some kind of set, and you can easily able to calculate that set. What you can do, you can take mod x common. So if you take minus mod x common, so mod x and minus delta, this kind of situation is there. So this is always negative. So if this is positive, then only I can tell that v dot is less than 0. Okay, so what happens, that when this become positive, then I have v dot is negative. So just you can write that this should be positive. Am I right? Anyone has confusion, then please let me know. Anyone has confusion? Because I am telling mod x is positive, so negative means this is negative, so this should be positive. So this should be positive means mod x minus delta should be greater than 0. Okay, if that is greater than 0, then I can tell that v dot is actually less than 0. Okay, now if mod x greater than 0, so if mod x less than 0, then what happens, v dot is positive. So outside of this set, there is no need to worry. Okay, because v dot is negative, but inside this set v dot is positive. Okay, so now what I am going to do, I am going to select some value that vx equal to c. Okay, and I am telling that in this particular set vx equal to c, when vx is less than equal to c, and c I have defined in this specific way, because I know that mod x is less than equal to delta, then what happens, v dot is positive, and when that is outside this, then that is negative. Okay, so I am going to substitute here, then I know that x in place of x I am going to substitute delta, then delta square by 2. This quantity is very critical quantity. Okay, after, if we are at this quantity, then I have neutral situation. But if you proceed like in this situation, then what happens, finally v dot become positive. Okay, so now what happens, that if you maintain c greater than equal to delta square by 2, it is possible to show that your whatever, if you start inside this set, you are going to remain in that set. Anyone has confusion on this? What I am telling, by plotting that, suppose something is decreasing. Okay, so if you are in this range, so you are trying to diverge, but do not cross this. So this is nothing but some kind of uniform bond or ultimate bond. Okay, so in this way, by showing v dot positive in some range and negative in some range, so whatever set I am going to formulate, we are telling that that set has some bond, and that bond is uniform bond, because all t greater than equal to t0, I am not going to leave this set. Anyone has confusion, then please let me know. Baby Dana, Iram,
Yes.
Is this point become clear? Why uniform? Uniform means that is valid for all t greater than equal to t0. And bound, because inside the region what we found that v dot greater than 0, but outside the region v dot less than 0. Okay, so what happens once trajectory is the nearby of the equilibrium point, at that time v dot greater than 0, so that try to diverge, but outside I have this kind of behavior. Okay, so due to that region that remains inside this. Okay, situation is not like limit cycle, please do not confuse. Okay, but situation in limit cycle trajectory is always going to live in this particular invariant set, but here I am telling that trajectory live anywhere, I don't know where that is going to lie. Okay, so this is a story about uniform bond, and now I am going to select the ultimate bond. Ultimate bond means how much possible, how much bond is possible. In previous case we have seen that based on the disturbance I have some kind of ultimate bond. Okay, so I can tell that ultimate bond B is not lesser than delta. So that kind of restriction I have. So similar kind of restriction whenever I have some kind of disturbance that comes into picture. Okay, so ultimate, whenever we are going to find the ultimate bond, then what happens, we have to find the Lyapunov set. Sorry, so V less than equal to C, and after that whatever epsilon, now whatever delta, so I will put x mod x equal to delta, so delta square by 2, so that will satisfy this kind of condition. Okay, so actually what happens, trajectory will monotonically decrease to epsilon, and after that they stop decreasing. Anyone has confusion, then please let me know, and after that they will enter inside this particular set. Okay, so we will see this kind of set construction in next part of the today's lecture. So what happens, so from the time solution cannot leave this set v less than equal to epsilon. Okay, so what happens, suppose solution is going to start in this set, and after that in presence of disturbance I cannot come to the equilibrium point, so I have some one Lyapunov ball is situated here, so that will contain, once we will give some kind of initial condition, and we are going to see that trajectory is deviate up to what much, what much amount, so that ball I have plotted, and inside that there exists epsilon ball, so trajectory will decrease to epsilon ball, and after that they will not decrease, and v dot less than 0, due to that reason we are telling that once trajectory is trapped in this set, that is not going to leave. Okay, and now I can able to calculate the uniform bond. So since v dot x is less than 0, due to that reason I can able to calculate the ultimate bond, not uniform bond, ultimate bond, and after that that bond is valid uniformly, due to that reason that is called uniformly ultimate bond. Okay, and how to calculate that bond, since we know that x is the the least value that will contain this, and I know that this is x square by 2 and less than equal to epsilon now. So what we will do, we will solve it, and after that I can find the ultimate bond from the Lyapunov analysis. Okay, so whenever we are applying Lyapunov analysis, at that time what we have to do, we have to see two situation, when v dot less than 0 and when v dot greater than 0. So once this situation is start, at that time I can able to pick that epsilon, and using that I can able to find the ultimate bond. Anyone has confusion, then please let me know. So now what I am going to do, I am going to give the definition, because most of time what we found that equilibrium point exists, but that is not at origin, that is changing with respect to time. So I have to change definition, because I don't know equilibrium point now, so I cannot tell that how to define stability about the equilibrium point. I don't know exactly, but what kind of assumption I have, I am assuming that equilibrium point, even if that is changing with respect to time, but that is going to lie in those region where my mathematical model is valid. And due to that reason, you can see here again I have started with non-autonomous system. I am assuming that there is piecewise continuous in T and locally Lipschitz in X in order to give guarantee that there exists a solution. And after that I am assuming that X belongs to D and D is subset of Rn and that contain the origin. Okay, origin means equilibrium point. Somehow I am talking about, I don't know equilibrium point. Okay, now I am going to define the ultimate bond, uniformly bonded. Okay, again, since we are not knowing the equilibrium point, due to that reason, I am not going to define now anything with respect to equilibrium point. Okay, we are telling that uniformly bonded if there exists a positive constant C. Okay, independent of T0. Okay, and what I am going to do, I am going to select A that is anywhere between 0 to C. So I have selected some positive constant C, and now I am telling that I have flexibility. I can set A anywhere between 0 to C, and corresponding to that A, if there exists a beta, and beta is function of A independent of T0, everywhere everything is independent of T0. Due to that reason, uniform name uniform comes into picture, independent of T0, such that now if initial condition T0 is less than equal to A, so it means that if initial condition remains bonded anywhere between 0 to C, I don't care about that, then xt I am telling that that is less than equal to beta and beta is function of A. So in this way we are defining the uniformly bonded. Okay, so xt is uniformly bonded means solution of this is uniformly bonded if they will satisfy this kind of condition. Okay, globally uniformly bonded if you can able to select A that is any larger value, any value you can select, still if this relation is valid, then we are telling that this is globally uniformly bonded. Okay, anyone has confusion in this two definition, then please let me know. Now let us come to the next definition, and this definition is uniformly ultimately bonded. Most of time during the practical expression or whenever we are writing paper, at that time we are using this definition, uniformly ultimately bonded. Okay, so what is meaning of uniformly ultimately bonded? So far we have seen that what is meaning of uniformly bonded and globally uniformly bonded. Now one quantity ultimate comes into picture. Okay, so what is meaning of this ultimate means ultimate name ultimate with ultimate bond B if there exists a positive constant B and C. Now you can see that I am talking about two positive constant independent of T0. Now again A I am varying in same interval 0 to C, like previous definition, uniformly bonded whenever I am talking. And now whatever time I am going to select, that time should be function of these two quantity A and B. Okay, so now what I am telling that A I am going to select between 0 to C, but now time is function of A and whatever second quantity B I have selected, and now xt is less than equal to A, then xt is less than equal to B, and this time is function of A, B means both A and B. Here if you see the previous definition, at that time I am just talking about t greater than equal to T0. Okay, but here I am telling that whatever time here, this time, after this time actually this bond is satisfied, then after means once transient, in another way, once transient period is over, then I can able to find this bond, and that bond is called uniformly ultimate bond. Okay, and globally uniformly ultimately bonded means if that is valid for any large A. Okay, so baby Dana, are you here?
Yes, sir.
So are you able to understand difference between uniformly bonded and uniformly ultimately bonded?
Yes, sir.
So could you please repeat what kind of information are you getting from uniformly bonded? What is difference? What is crucial difference?
Sir, the time limit.
Actually, main theme here, here difference is that whenever we are talking about uniformly ultimately bonded, at that time we are going to wait for some time such that transient is going to occur. Okay, but if you see the previous definition, in that definition I am not going to wait. Okay, I am telling that from initial time onward, t0 is time when I have started the experiment. From time, that time onward I have this kind of relationship. But here you can see that here I am waiting, and I am telling that after this finite time, and that is function of a and b. So a, if you select 0 to c anywhere, so that is depending obviously on that, and b, then this situation will satisfy. That is the difference between those two. Okay, so in one, whenever I am talking about uniformly bonded, at that time I don't care about the transient, or I am not distinguishing the difference between transient and steady state response. But whenever we are talking about uniformly ultimately bonded, at that time we are distinguishing these two differences. Okay, anyone has confusion? Now if you are able to understand these two difference, now what I am going to do, I am going to see again the Lyapunov analysis for bondedness and ultimately bondedness, and again in this process I am going to involve the nonlinear system also. So I am going to give some generalized framework. So I am going to take some kind of non-autonomous system, and after that what I am going to do, I am going to see the Lyapunov analysis, what kind of information I can gather from the Lyapunov analysis. So again I am going to consider the Lyapunov function. So I am assuming that that is continuously differentiable and positive definite. And after that, what we found that whenever we are constructing Lyapunov function Vx, that that is always somehow, if you see in terms of ball, so you might have seen that they will give the compact, some kind of compact set. So I have defined that kind of closed and bounded set by this symbol is called wedge. So wedge symbol, and after that I am telling you can take any symbol, that that is just optional. And after that Vx, since now I cannot tell that Vx is going to decrease to the 0, so I am telling that Vx is decreased up to epsilon value, and epsilon is less than C. And after that, what I am going to assume, in this particular region, means in wedge region, actually I have this kind of things. V dot less than equal to, here time dependent Lyapunov function is also allowed. Okay, in previous class I have told you that whenever you have non-autonomous system, either you can take the time invariant Lyapunov function or time dependent Lyapunov function, that doesn't matter. Okay, and Wx is continuously positive definite function. Okay, so this kind of situation I have. Now you can see here that since this inequality is valid in that region where I have Lyapunov ball, so I can able to define now two set. One set is omega c and one set is omega e. Okay, and I have cascaded all set. Here you can see that I am drawing some kind of region where these inequality and this inequality is satisfied, and here you can see that I have this ball, and after that I have omega c ball. Here I am not plotting x, please be careful. Okay, whenever you are plotting x in the previous class, at that time I have reverse kind of inequality. Here I am plotting Vx just. Okay, so now if you plot this, then you can now see that I have two ball, and this region, this particular region I have defined as a wedge region. Okay, and wedge function I have, wedge region I have defined, wedge set I have defined like this particular way. Okay, and in this whole region, what kind of property is there, that Vtx, that is strictly negative by some kind of positive definite function. That kind of things I am assuming. Okay, so if that kind of situation, so if I start in this region, I am not going to leave. Okay, so this set is closed and bounded, so compact set. So what I am telling that since V dot is negative in wedge region. So any trajectory starting in wedge region move in direction of decreasing v. Okay. Now what I am going to do, I am going to apply the two theorems whatever we learned during the previous class, that is uniform stability and uniform asymptotic stability. So I am just going to recall that two theorem. I have written the same theorem whatever we have learned in the previous class. I am telling that suppose I have non-autonomous system, x equal to 0 is the equilibrium point and my mathematical model is valid in this region. Okay, and I have defined some kind of Lyapunov function that is continuously differentiable and that is bounded by two continuously positive definite function wx1 and wx2. Okay, so could you please recall the name? What is name for this? Vtx less than equal to w2x. Sunidhi, could you please tell me that what kind of name I have used when Vtx is upper bounded by some w2x and w2x is positive definite function. So what kind of name I have used in previous class? Iram?
Sir, decrescent.
Yeah, this is called decrescent. And Sunidhi, could you please tell me that what is name for this?
Sir, positive diff.
Yeah, that is called
Positive
positive
definite.
definite. So this is called positive definite. So actually why I am repeating, because several times if you learn the literature, then people directly using this kind of name. Okay, so you have slowly you have to become comfortable with the name. Okay, now if this relation will satisfy, then we are telling that is uniformly bonded. And in previous class we have also seen that if this kind of condition is satisfied, then what kind of k class function that comes into picture. Okay, so in previous class we have already seen that vtx so is less than this, means because v dot is less than 0. So we have already seen, so just for the completion or just for the recalling purpose I have written this. And any positive definite function is bounded by k class function. In previous class we have seen, and from this I can able to now establish the inequality. So xt I have taken, then alpha inverse, and after that alpha inverse and vtx because less than equal to 0, and I know that is alpha to xt0 by putting xt0. So this is the bond. So solution is actually bounded by some kind of, this is k class function because alpha is k class function. So alpha 1, this is alpha 1, alpha 1 inverse is also k class function, and alpha 2 is also k class function. So composition of two k class function is again a k class function. Okay, now what we have seen in the previous class, if now this inequality that v dot tx in place of 0, if I will able to substitute more strict condition, then that is called minus w3x, and w3x is continuously positive definite function. Then what happens, I can tell that this solution xt is now bounded by some KL class function. Okay, and if you see the previous lecture, at that time I am telling that okay, if I have some kind of output region, that is output ball, you can tell that is x less than equal to r. So and that is subset of D that I have defined like this. So most of time I am defining like this. So this region is called BR and this space is called D. So inside D I have BR, and after that what happens, that I am going to construct Lyapunov function in this particular region, because this region is only interesting for me, and due to that region I am defining the region. And in previous class we have seen that if Vx is bounded by w1x and w2x, and if you extract x from here, then this ball is larger ball and this ball is a smaller ball in terms of x. Okay, and due to that reason I am going to calculate the minimum value of w1 because I want to select the outer ball. Anyone has confusion on this, then please let me know. And what I am telling, that if you start from the lower ball means now input ball, then you are not going to leave the output ball, and after that this kind of k class function comes into picture. Okay, and and if d equal to rn and w1 is radially unbounded, it means that I can select initial condition anywhere in the space, then that is globally uniformly bounded. Okay, so here basically I have used wrong inequality. Inequality that is not inequality 17. Basically, that is inequality. This inequality I am talking about inequality number 5, that Vtx is bounded by two continuous positive definite function. So if you see 5, so here in place of 17 I have 5 and 7. If you see the 7 is that means rate of change is bounded by some kind of continuous positive definite function. Now what happens that if I see this region is wedge region. So wedge region I am telling that how basically we have defining the wedge region. If you remember that Lyapunov function Vx is lie between C to here. You can see Vx lie between minus epsilon to C, and I have told you that due to some perturbation, due to some disturbance, what happens, Lyapunov function is not decreasing to the zero. They are going to, after some time they stop decreasing. Okay, but in this set, in this wedge set, actually Lyapunov function, because V dot Tx is actually less than 0, and here a strict condition means less than like this, and due to that reason trajectory is going to decrease in this region. Okay, so we know that in this wedge set I have some decrement of trajectory, and due to that reason I have written here that these two inequality means Lyapunov function and 7 means W means rate of change is bounded by W3x, that is satisfied, and V is the Lyapunov function. Okay, and now trajectory behave if the origin was uniformly asymptotically bounded, if this kind of condition is satisfied, if exactly I know the equilibrium point. But here situation is that I don't know the equilibrium point. So what kind of things I have to show, that suppose if I have two region, and it is better that try to understand from the scalar case. So I have started with this particular system minus x plus delta sin t. So what we are telling that now as trajectory is here, so what happens that is decreasing because x is greater than 0 and x dot is less than 0, and this quantity is going to become dominate over this quantity. So we are decreasing. After that we are telling that in finite time I am going to enter inside this region, and once I enter inside this region, now I don't know that I am moving like in this direction or this direction. Okay, so first what we have to prove that in finite time I can enter inside this region, and once I will in this region, you know that this is invariant set, so I cannot able to leave that region, and due to that region this is uniformly ultimate bound, because I will wait for finite time to enter inside this region. Okay, so somehow I am talking about the steady state response. Okay, so similarly, once trajectory is moving, their corresponding mapping is also moving. Okay, so how basically we have established the mapping using Lyapunov function. Okay, so I am telling that is lie between V is lie between like this. Any confusion, then please let me know. Any confusion? So now what I am telling, initially I am talking in terms of trajectory. Now I start talking in terms of Lyapunov function. Okay, and Lyapunov function is nothing but mapping from x to Vx. Okay, so now again similar kind of situation, if you see the in terms of ball, then what happens that I have something, this is V epsilon, this is Vc, and what happens, this region is the wedge region. Okay, and here V dot Tx is actually less than W3x. Okay, so once trajectory is here, then that is decreasing, and once that will come in this region, they will not come out from this region. Okay, so same kind of things I am going to see here. So first I have to prove that they will enter in this particular region omega epsilon in finite time, because once they will enter, then they will not going to leave. So first I have to prove that will enter. Okay, so how what at what rate they are entering, so V dot equal to W3x. Okay, so what I am going to do, I am going to calculate the minimum value, minimum rate of change. Okay, so rate of change of quantity, and what I am going to do, I will take the minimum of this on this whole wedge set. So in this whole set, what I am going to see, I am going to see the rate of change of v, means velocity v you can interpret as a position vector, then v dot as a velocity vector. So I am going to see the minimum velocity. Okay, I don't know the velocity, exact velocity, so I will select minima, and after that we are telling that even if that will move with minimum velocity, then they will enter inside this region infinite time, and due to that reason I have defining minima over all wedge region, and w3x I have selected. Okay, and after that, since w3x is positive definite function, this, if you see this function, this is positive definite function, and with negative sign, that is negative definite function, we are telling that w3x is greater than k for all x whenever that is in this region, wedge region. Okay, because this is positive definite function, so that is greater than equal to some positive value whenever we are in this region, because positive definite function is 0 only when x equal to 0, but we are telling that I am not in this region, I am in this region. Due to that region, this relation will also always satisfy. So if you will substitute here in place of w3x, you can see that I have this kind of inequality now. So now rate of change is less than equal to some constant number minus k, and this inequality is only true when x in this wedge region, so that is not true always, so please be careful. Okay, so only in this region, black region, I am taking the telling that vtx is less than equal to minus k, and when vtx is less than equal to k, so I have now very simple equation, dv by dt equal to minus k. So what is solution for this equation? V equal to vt0 minus kt minus t0. So similar kind of things I have written. Anyone has confusion on this, then please let me know. And now when we are decreasing, and I am telling that this region v dot tx is less than 0, so as time is moving, we are decreasing towards this ball, and that ball is omega epsilon, and we have started with omega c, and due to that region you can see that I am moving from c, so vx0 is nothing but c, this actually radius of this ball is c, and radius of this ball is epsilon, so due to that region I have substituted c. Okay, now you can see that finite c is some finite number, and this number is increasing as t tending towards the infinity. Okay, and due to that reason, now after finite time it is possible to show that this is reduced to epsilon. Okay, I can easily able to calculate, just in place of vtx I can substitute epsilon, and after that I can calculate the time, at what time basically this trajectory will enter inside this ball. Okay, yeah, inside ball. Anyone has confusion on this? So if you see the time, time is always finite. Why time is finite? C is finite, epsilon is finite, and k is finite, and due to that reason time is also finite. Anyone has confusion, then please let me know. Why I am claiming that in finite time I can able to enter inside this region, and once I will enter, then I cannot leave. Okay, now we know that in finite time I can enter inside that. So now what I am going to do, I am going to see that case when v dot minus w3 x, and I am going to select some kind of region mu, and here I am assuming that x is lie from mu to r. Okay, and set wedge is the non-empty and contain inside this. I am assuming that whatever wedge set I have constructed, or whatever Lyapunov ball I have constructed, that is going to lie inside this. Okay, and for that particularly I can select k class function, because vx is bounded by two positive definite function, positive definite continuous function, and whenever that is bounded by positive definite function, then there exists k class function, and due to that reason I can write like this, and after that now I can able to find the estimate of solution using this k class function. Okay, we have done this kind of analysis several times, so I think that you are able to understand this. And c is alpha 1 r. Okay, because somehow I have to calculate the radius of this particular ball, radius of this ball c, and from here by k class, with k class function I can able to find that c, and c is nothing but alpha 1 x, and from this we are able to correlate between the actual trajectory x or solution trajectory with that Lyapunov ball C. Okay, now taking C equal to alpha 1 r, that ensure that omega C belongs to Br, because I have to make sure that whatever Lyapunov ball, that is actually inside the output ball. So if I select C like C using some kind of K class function, I can give in surety, because I know that Lyapunov function is bounded by two positive definite continuous positive definite function. Okay, and if x is less than mu, so at that time Vx is actually bounded by alpha 2 mu. So I can calculate the upper bound and I can calculate the lower bound both. Okay, now now what I am going to do, I am going to construct the set here. You can see carefully that whenever I am constructing set, first place I am constructing in terms of VC, but here I am constructing in terms of the trajectory. Okay, and whenever I am doing construction in terms of trajectory, then and suppose Vx is bounded by some kind of alpha 1x and alpha 2x, so and if you are plotting x, then this side ball is coming here and this side is coming here. Okay, we have already seen in previous class. Okay, so similar kind of situation I have. Omega C is the basically nothing but the Lyapunov ball I have, and after that I have some kind of ball that is epsilon ball. Now what I am going to do, I am telling that I have some kind of beta b, where beta b is the ultimate bond, and beta mu I am going to start. I am going to select the initial condition. Okay, so that kind of construction I have. So in this way I have constructed now, and now you can see here that since Vx is going to lie in this and Vx is less than equal to epsilon, and after finite time they will enter inside this ball, at that time I can tell that x is given like this. Okay, and epsilon is, if you see the epsilon, then alpha to mu, because if you see Vx, then that is bounded by alpha 1 x and alpha 2 x. So what happens that their minimum value is went to the mu, and due to that reason, in order to construct the lower ball, I have to see this quantity. Due to that reason, I have substituted mu here. So alpha 2 mu is here. So finally I can able to tell that this is the ultimate bond. Okay, so now proof is little bit involved, but whenever you are doing the calculation, then things is very easy. You can see the Lyapunov function, just you can see the K class function, and in order to calculate the ultimate bond, okay, now what you can do, you can just solve this, and this will give you the ultimate bond. Okay, so using one example we will see in the later part. First we will complete the proof. So now theorem is that, suppose I have Lyapunov function, and Lyapunov function is actually bounded by 2k class function, and rate of change is positive definite function. Okay, and after that, if I will select r greater than 0 such that output ball is going to lie inside this region D, same kind of things I am telling, and I have selected mu. Okay, mu, if I will select uniform ultimate, first I have to select the bond, and after that we have to say so that trajectory is going to live inside that bond or not. It is possible to show that if I will select mu like this, then there exists a class K function xt0 that will satisfy this kind of things. Now I can show that xt0, if I will select like this, then I can show that for t greater than equal to t0, all solution trajectory is converging like this for all t greater than equal to t2 t plus t0. Okay, like this. Now now what I am going to do, and we know that xt, if this condition is satisfied, then what is ultimate bond? So we have just actually seen ultimate bond from here, from this relation. So same kind of things I have actually quoted in terms of the theorem here. Okay, now I am going to take one example. So up to here, that is theoretically involved. So main theme you have to understand that I have some kind of Lyapunov ball, and if I will fix the ultimate bond. Okay, and how basically one can fix the ultimate bond? By seeing the Lyapunov function. So I have k class function here. Okay, so you can see the ultimate bond, and how basically we are calculating the ultimate bond. Ultimate bond you can see carefully that I have selected by this relation alpha 2 inverse alpha 1 x in that way, and in that way I am selecting. So once you select that, then it is possible to show that trajectory will decrease and they will enter infinite time in this region, and after that they are not going to leave. Okay, that is the whole story. And if here alpha 1 and alpha 2 is k infinity class, then obviously that is true for for the any initial condition. So what I am going to do now, I am going to select a second order system, and here I have selected some kind of Lyapunov function x transpose px. Okay, and P is some kind of positive definite matrix I have constructed, and after that I am going to calculate the derivative. Okay, and it is possible to show that some specific construction of P, that V dot is given like this. Okay, so finally this kind of relation comes into picture because x1 and 2x1 is sign indefinite, so I have used the not. Okay, after that you can see that this term is negative, this term is negative, just this term is going to difference create some kind of problem. So what I am going to do now, I am going to make this part which is going to dominate over this part. Okay, and due to that reason I have divided this part, negative part, into two way, 1 minus theta and theta into x square. Okay, now what we are going to do, we are telling that if this whole quantity is less than 0, then this inequality less than 0 will satisfy. In that way, now you can see that I am able to find the ultimate. I am able to find some kind of condition on x. Okay, and now once you find the condition on x, that is nothing but some kind of mu. Okay, now what we are going to do, whatever Lyapunov condition I have formulated. So Lyapunov condition I have formulated by x transpose px. So you can use the Rayleigh inequality. So you can see I have used the Rayleigh inequality here. So lambda mean p x square, and this is half x power 4, like that. Now I am going to construct two function, two KL class function, so that such that I can take the, tell that this is bounded by to class k function. Okay, so x transpose px plus half x 2 square power 4 is there, and we know that the lower bound x transpose px, that is less than lambda mean p, like this, lambda max p and x. This kind of situation I have. So I will neglect this and I will select minimum value like this. Maximum value obviously I have to add this. So half x power 4 is there. So in this way I have selected the k class function alpha 1 and alpha 2, and once k class function is selected, then I can find the ultimate bond by solving this inequality. You can see here by same relation, by this relation, like this. Okay, so now first you have to understand the theorem, so please again go through that. After that, second step is you have to construct any Lyapunov function, and you have to show that Lyapunov function is not always decreasing, but at least that will decrease in some region. You can see here that how basically I have constructed this region x2, that is greater than m root 5 by theta. It means that trajectory is not going to decrease beyond this, or inequality v dot x is not satisfied beyond this. In that way you can select the region mu. It means that in this region mu I can give guarantee that v dot tx is less than 0, and after that what you can do, you can now see the Lyapunov function, construct the upper bound and lower by using k class function, and after that ultimate bond you know that is given by the combination of alpha 1 alpha 2 and whatever mu you are able to calculate from the here. You can see this is nothing but mu. Okay, so with help of this you are able to understand that Vtx is decreasing, and with help of k and kl, with help of k class function, you are able to make some kind of this function alpha 1 inverse alpha 2, and just you can couple here, and I have actually just substituted, and if you substitute, then in this way we can calculate the ultimate bond. So applying theorem is not a difficult task. You can take any system, any nonlinear system, construct one Lyapunov function, calculate the bond of Lyapunov function in terms of k class function to k class function, see where Vtx is decreasing, okay, and based on that decreasing region you can find the mu, and you can in composite function you can just put the mu, then you are able to find the ultimate bond. It means that once transient is over, then trajectory is going to settle in this particular range, that is the meaning. Anyone has confusion? So sorry for the little bit longer class, okay, but this topic is very important, because most of time what happens that whenever you are doing some kind of analysis, at that time you have to calculate the ultimate bond, where finally after once transient is over, then where trajectory is going to settle down. Okay, most of time what happens, I don't know the exact equilibrium point. Okay, at that time this kind of analysis or this kind of definition plays a very important role. Okay, so what now you can do, please go through the Khalil book and try to understand this part. Okay, so everywhere just calculation is involved, but idea is again very simple, whatever. So please remember, so if you see the development of Lyapunov function, everywhere we are using the same concept. What kind of concept we are using? We are constructing one ball where mathematical model is valid. We are trying to keep our trajectory in some ball. We are defining BR. After that, we are constructing some kind of Lyapunov region here. And wherever I have some kind of ultimate uniform bonded kind of situation, then this Lyapunov region is again bounded by two different regions. Okay, now what we are going to do, we are going to construct some kind of input ball here, and we are going to show that trajectory is going to where trajectory is going to remain there. So everywhere this kind of situation means situation we are dealing whenever we are proving something. Okay, so due to that reason you have to understand carefully the Lyapunov proof. Then all other thing is just consequence of the calculation. Okay, so with this remark I am going to end the today's lecture. If you have any question, then please let me know.